Welcome to the Advanced Power Supply Topics web seminar. I am Bill Hutchings, a Product Marketing Manager for Microchip. This is the agenda for the course. We will discuss issues that affect the reliability and saleability of switch mode power supplies. Inrush current and soft start functionality affect the turn-on stresses of a power supply. Input transients refer to externally generated excessive voltage pulses that can damage a switch mode power supply. Low or high input supply voltages are problems handled with under and over voltage lockout functions. Power supply output over voltage and over current conditions need to be considered. Voltage trimming, remote sense, and power supply sequencing are topics that affect the output voltage at the user's board. In large fault-tolerant systems, load sharing among power supply modules is required. To sell power supplies, EMI, electromagnetic interference issues must be considered. When a power supply is first plugged in or turned on, there is a large current surge into the power supply as the input capacitors are charged. Current inrush causes the arcing noise often heard when a computer or other device is first plugged into a wall socket. Current inrush is stressful on switches, diodes, capacitors, wall sockets, etc. Many power supplies incorporate inrush limiting. The most common method is the NTC, negative temperature coefficient resistor. The NTC resistor has a high resistance of about 40 ohms when cold and a low resistance of less than 1 ohm when hot. The NTC resistor is placed in series with the input to the power supply. The cold resistance limits the input current as the input capacitors charge up. The input current heats up the NTC and the resistance drops during normal operation. If the power supply is quickly turned off and back on, the NTC resistor will be hot, so its low resistance state will not prevent an inrush current event. Another method is to use triacs or relays in parallel with a resistor. The resistor limits inrush current. A sensor circuit monitors the input capacitor voltage. When the input capacitors are charged, either a relay or a triac across the input resistor is enabled to provide a path for power flow during normal operation. Active power factor correction, PFC circuits, also minimize inrush currents by minimizing the size of the input capacitors directly connected to the power input terminals. Soft start is the process of actively controlling the power supply so the output voltages rise at a controlled rate at power on. The soft start process limits peak currents that normally flow to charge capacitors in the power supply and the attached load at power on. The controlled soft start process reduces stresses on components and helps reduce input current inrush. A hard start or non-soft start power-up process will generate severe current loads that cause acoustic noise from components such as transformers and capacitors that are audible to the customer. Hard start power supplies can experience high voltage overshoot on startup. Lightning and electrical equipment on the AC power lines can generate very high voltage spikes between 1 to 20,000 volts, lasting from a half to 50 microseconds. There are several types of devices used to limit the input voltage transients. The most common transient protection device is the MOV, or metal oxide semiconductor, also called a varistor. MOVs clamp high voltages by becoming a low resistance when a high voltage is applied. MOVs are inexpensive and can absorb a lot of energy. The relatively high on resistance means the clamped voltage can still exceed 1,000 volts. MOVs have a wear-out mechanism with repeated energy absorption events. They fail shorted and therefore they must be fused. Transorbs are basically power Zener diodes. Transorbs offer very high speed and tight voltage clamping characteristics. Transorbs have limited energy absorption and are expensive. Gas-filled surge suppressors can clamp very high energy surges, but the clamping voltage may be several times their rated voltage. Once a gas-filled suppressor arcs and conducts, they will continue to conduct until the input voltage is removed. When used on an AC power line, the alternating voltages usually commutate the arc. Gas-filled devices are not used on DC power lines. Many systems use combinations of these devices to obtain the desired surge protection. Power supplies usually incorporate circuitry that inhibits the operation of the power supply if the input supply voltage is too low or too high. Low input voltages are stressful to a power supply because the input current rises as the input voltage drops. Most AC power supplies have a lower input voltage limit to prevent overheating of the internal components. Excessively low input voltages can cause faulty operation of the control circuitry and insufficient gate drive voltage to the MOSFETs and the IGBTs. High input voltages can damage transistors and other components as their voltage ratings are exceeded. Be wary of switching generated transients, which a high input voltage condition may exceed the transistor specifications. When the input voltage to a power supply is out of specification, the safest response is to turn off the power supply until input conditions improve. Overvoltage circuits provide protection for the load in the event of failure of the power supply. A crowbar circuit typically includes a silicon-controlled rectifier, SCR, a fuse, and a voltage sensing circuit. If an overvoltage is detected, the SCR is turned on to a conducting state, and the current from the power supply flows through the fuse and the SCR into the power return line, the ground line. The fuse is sized to blow at the maximum current rating for the power supply, but not at the normal current load experienced by a functional system. Fuse tolerances are quite wide, so the power supply must be rated for more current than the required by the load to ensure that the fuse will blow when the crowbar is activated. The cost of providing a crowbar circuit and associated cost of a power supply with a higher current rating load must be weighed against the cost of destroying the load if a power supply failure occurs. There are four basic behaviors a power supply can provide in response to an overcurrent situation. 1. The power supply can immediately shut down and then periodically check to see if power can be restored. This is the auto restart function. 2. The power supply can tolerate the overload for a period of time before it shuts down, perhaps a few minutes. This is thermally limited. 3. The power supply can enter a current limited mode. The full rated current is delivered to the load. The output voltage is determined by the load current and the impedance of the load. An issue with this response methodology is that the power supply is providing high power to a load that may have experienced a failure. This could become a fire hazard. 4. The power supply enters a power limited mode. The output voltage is reduced, but controlled, as the output current grows. The goal is to limit thermal overload. This mode is useful where the load can tolerate a voltage drop. Voltage trimming is often supplied on a power supply to enable the user to adjust the output voltage slightly to compensate for system wiring voltage drops or to compensate for unit-to-unit variations of the power supply. The voltage trimming is usually implemented with a potentiometer that the user adjusts with a screwdriver. Remote sensing uses additional wires from the power supply to the load to sense the voltage at the load. These sense wires are called Kelvin connections. No appreciable current flows through them, so they do not experience any significant voltage drops. Remote sensing compensates for voltage drops across the system wiring between the supply and the load. The remotely sensed voltage modifies the power supply output voltage over a limited range, typically plus or minus 3%. The voltage adjustment range is limited to ensure an open remote circuit does not produce excessive output voltages that might damage the load. Many electronic devices require their multiple supply voltages be coordinated at power on and off to protect their circuitry. If the supply voltages are improperly applied, many integrated circuits can experience latch-up, a destructive process where internal semiconductor junctions become forward biased, resulting in uncontrolled current flow. Other systems require that specific circuitry be powered prior to a known safe state to the rest of the load circuitry. The most common power supply sequencing method is the simultaneous ramp up and down. The choice of power sequencing is very dependent on the system requirements. Load sharing connects the outputs of two or more power supplies together to power a load. Usually there are more modules with more total power capability than required by a system. The amount of redundancy is dictated by system reliability goals. If a power supply module fails, the remaining modules continue supplying power to the system. The user can remove failed modules and install replacements without powering down the system. Load sharing is often a requirement for large computer system power supplies where fault tolerance and high system reliability is a necessity. Ideally, all of the modules should share the load equally. By operating at reduced workload, assuming redundant capacity, the reliability of the power modules will be increased. Slight differences in component values and wiring resistances cause the output voltage at some modules to be slightly higher than others. Even if the voltage imbalance is only millivolts, the result is that some modules hog the load while others are lightly loaded. The heavily loaded modules run hotter and will probably fail earlier. The remainders carry more of a load, and you can start creating a domino effect. A slow analog or digital communications link passes information among the modules to force the output voltages to a common value to enforce load sharing. The control loop is slow, working on a thermal time constant basis. Around the world, there are many government agencies and standards bodies that regulate conducted and radiated emissions of electronic equipment. Europe, with the rise of the EU, is migrating to a unified IEC standards. Consult with experts on what applicable limits are for your markets. The switch mode power supply, with its high frequency switching and high power levels, is by nature a powerful emitter of radio frequency noise. The chart shown in this slide is illustrative of the typical limits imposed on power supply designers and manufacturers. When the tests are performed, the RFI receiver has a fixed bandwidth, typically 9 kHz wide when scanning from 150 kHz to 30 MHz, and 220 Hz when scanning below 150 kHz. The limited measurement bandwidth is important in understanding the value of dithering or spreading the noise emissions over a wide frequency range to reduce the average noise power per hertz of bandwidth. While the total emitted noise energy does not change, the measured peak values will be reduced. EMI filters for switch mode power supplies typically include circuit elements to attenuate both common mode and differential noise. The most common low-cost filters incorporate the X-gap for differential noise suppression, the common mode choke, and the Y-cap for common mode noise suppression. For applications that require more attenuation of EMI, complex filter designs incorporate multiple instantiations of common mode and differential filter elements. The Y-cap enables AC current flow to the ground's connection. This current is called ground leakage. The Y-cap ground leakage is an issue in medical applications where ground leakages must be kept very small. Safety agencies have standards that limit ground leakage currents to levels that are considered safe for the general public. The major contributor to ground leakage currents are the common mode filter capacitors called Y-caps. The need to limit ground leakage currents limits the minimum impedance of the Y-cap capacitors and therefore their effectiveness in combating common mode noise. Some types of medical equipment have much lower limits. Meeting medical leakage current requirements can be difficult because the parasitic capacitances between the circuit components and the enclosures can add significant leakage currents. For more information, here are references to some important documents that contain a lot of information about the DSPEC30F family of devices. The family reference manual contains detailed information about the architecture and peripherals, whereas the programmer's reference manual contains a thorough description of the instruction set. For device datasheets, family reference manuals, and other related documents, please visit the following Microchip websites. Thank you for attending this webinar.